oggi perché purtroppo manca sia Maurizio che Juan Campos, e comunque il mio piacere introdurre Tatiana Tommasi, che sarà lo speaker di oggi. Una breve presentazione, qualcuno di voi già conosce Tatiana perché si è recentemente unita al nostro dipartimento come ricercatore è anche affiliata all'Istituto Italiano di Tecnologia. Ha ricevuto il suo PhD all'EPFL, dopodiché ha lavorato come assistente, come ricercatore all'Idiap Research Institute in Switzerland e come postdoc all'Università di Dauin e all'Università di North Carolina in Chapel Hill. E prima di unirsi al nostro dipartimento è stata ricercatrice presso l'Università della Sapienza di Roma e ricercatrice all'Istituto Italiano di Tecnologia. Il suo lavoro di ricerca è focalizzato principalmente su computer vision e machine learning, con particolare interesse sull'ambito del knowledge transfer e domain adaptation. Il titolo della sua presentazione è Domain Adaptation e Domain Generalization Techniques, Adaptive Learning Across Categories and Domains.
Grazie per l'introduzione, mi sentite? Sì. Allora, di nuovo grazie per l'introduzione, grazie di essere venuti alla talk. Io, come diceva Andrea, lavoro nell'intersezione tra computer vision e machine learning e in particolare mi occupo dei topic di learning adattativo. Ed è esattamente quello di cui vi parlerò oggi. Learning adattativo, quindi si tratta di nuovi problemi, nuove categorie e nuovi domini. Allora, giusto per dare una proprio introduzione base, abbiamo detto che lavoro appunto all'intersezione tra machine learning e computer vision. Che cos'è il machine learning? Diamo una definizione proprio base della base. L'idea è che definiamo degli algoritmi che aiutano un computer a migliorare nell'eseguire un determinato task, quindi a migliorare la performance di un determinato task a partire dai dati, quindi dall'esperienza, un po' diciamo come noi intendiamo l'apprendimento, quindi come noi intendiamo imparare. Vediamo un esempio pratico proprio perché parliamo di immagini. Supponiamo di dover distinguere tra cani e gatti. Abbiamo tante immagini di cani e di gatti etichettate. L'idea è di trovare appunto un metodo per capire, data una nuova immagine, se si tratta di un oggetto appunto di un cane o di un gatto. Ora, se pensiamo in termini, diciamo, come noi esseri umani, possiamo cominciare a fare delle descrizioni di questi tipi di animali, quindi sulla base della lunghezza dei baffi.
Posso venire?
Oh, sorry. Okay. Yeah. So I
for intro.
Yeah, sure. Okay, so I work at the intersection between machine learning and computer vision, and the idea here is to give you an overview of the techniques about domain adaptation, transfer learning, domain generalization, and in particular I will start just with a brief description of what is machine learning. So the idea is that of defining algorithms that help computers to improve their performance at a certain task on the basis of the data, on the basis of experience. So more data, more experience becomes also better performance. So let's say that we want to give an example of distinguishing between cats and dogs. We have images which are annotated, and we want to define an algorithm to separate them such that when we have a new sample, we will be able to define guess the associated label. So if we think about, let's say, in terms of humans, we can describe cats and dogs on the basis of the, let's say, of the mouth, the dimension of the ears, or the tail, how tall they are, the fur, and so on and so forth. All this description becomes some sort of numbers that we can collect and then plot into, for instance, very simple bidimensional plot. So the idea is that once we have plotted these points, we want to find an algorithm that separates them, right, for a line or somehow a way to group the samples such that on one side we have cats and on the other we have dogs. And at this time, given a new sample, we want to be able to recognize this new image and associate it. Now, this is something, standard, and again, so if we think at the human level, we describe these attributes or characteristics of the animals. If we think at computer level, what the computer has to do is to analyze the pixels the image and extract some sort of information. So till a few years ago, the idea of extracting feature was something that was done by hand, or at least with some specific characteristics starting from some let's say human or engineering level description, and then these features were given to an algorithm that was performing the classification. But recently we know that there is this big boom about deep learning, and so what actually changed is that we are directly feeding the network or feeding the algorithm with the images and letting the algorithm itself extract the most important information, the most important features to understand then at the end if an image is a cat or a dog in this particular case. And we know that the features which are extracted at different levels of the networks start from just simple corners and edges to some more complex, let's say, texture or structure, till ending into something that looks like parts of the objects. And then by exploiting this kind of information, we have finally the classifier which defines if the image, so which is the label of the image. Now, this is something standard nowadays, and we know that there are deep learning models that perform even, get performance even higher than what a human can do. You have seen, I think that everybody knows this AlphaGo challenge that Deep Blue actually beat the champion in this game. But even though there are some tasks where deep learning are performing exceptionally well, there are some others where still they are lacking in their capabilities. So think about this particular case. So if we have trained a network with this kind of images, very clean, so the object is in the center of the image and the background is, let's say, plain or homogeneous, and what happens if we give then to this network which is trained some new kinds of images? So let's say that if they are still pictures, maybe with no more just one object, but multiple objects, a little bit cluttered, and the background is no more uniform, it might be some difficulties, there might be some difficulties, but still it will be quite good to identify what are the objects, and in particular to recognize that there is a cat in that image. But if we give the network something more high level, something like a painting or a sketch, which still for us as human contains a cat, so at the semantic level is still containing the same category, well, the network will not be able to perform well. It will start making a lot of mistakes, because actually what happens is that the support of the image, so the information, the way in which it is extracting information from the image itself, since the signal is different, at the end of the day it will not be able to recognize what is the content. So this is something that holds not only for object classification, but even for, let's say, other tasks. Think about the case in which you don't want to annotate, give a label to the whole image, but to give a label to a single pixel in an image. For instance, semantic segmentation for an urban scene, or you can think about images that are collected by, I don't know, an autonomous car going around your city, right? So you can have a lot of images, collect images even across different cities, across different countries, and then you train your model to be able to annotate these images. Well, if all the images are collected in daylight, well, your network will suffer again if you give to the network an image taken during the night. Or in case of severe weather condition, raining, if it's foggy or if it's snowy, and so, for instance, part of the image or part of the objects in the image are not visible anymore. Well, this kind of task means that, so this kind of evidence means that deep learning, which is nowadays considered some sort of synonym for artificial intelligence, well, it's not really intelligent yet, right? Because if you look at all the definition of intelligence nowadays, I mean, there are many definitions of intelligence, but there are some works that try to summarize what is the hallmark of human intelligence, for instance. And it turns out, I mean, there is a high-level definition which says that an intelligent agent is able to adapt and achieve goals in a wide range of environments. So this kind of situation is not still true for deep learning, and we still need to work to make it able, so deep learning, to make it able to generalize and adapt also to new kind of situations. How can we do that? Well, the point is that we have to go to, starting from the definition of machine learning that I gave you before, so what is learning, the fact that we have algorithms that improve with data, right? We have to pass from this first level of learning to the second level of learning, the ones that improves not only with data, but improves also with experience. So the more tasks you see, the better you become able to learn, and you learn also faster. Now, the second level of learning actually has a lot of names: learning to learn, meta-learning, lifelong learning, but are all the components that actually help us making system more and more intelligent. And what is the effect? The effect is that we reduce the amount of label information needed. So when we encounter a new task, we don't need a lot of annotated samples to define a model. We can leverage our previous experience and learn faster. And then the model that we define, it will also have less parameters, exactly because we can exploit previous knowledge. And somehow, since we are composing knowledge from previous steps, so we are defining a structural knowledge, one step after the other, we also have a way to, let's say, improve explicability in the process in the whole learning process. Now, this is something useful not only for instance, for the baby robot iCub, which is able to grasp a ball and then also uses this experience to grasp an apple. But it is important also for many other applications. Think about a robot in a production line. What happens if the product changes, or if you have to repurpose the same robot in a new production line? And again, as I explained you, I mean, the example that I gave you before, it is also important for autonomous driving. We cannot expect to retrain a model every time that the weather condition changes. So we need to be able to adapt. So in this, let's say, big area of learning to learn, lifelong learning, etc., some frameworks have been well defined, some sub-areas have been studied, and we have some definitions. So let's say that we can consider two high-level frameworks. One is transfer learning, and the other is online, incremental, and active learning. So let's say that transfer learning deals with all the process related to adaptation regarding new categories and new domains, so how to avoid starting from scratch at any new task and adapt, but is not strictly related to the time axis, so to the dynamic part of learning. Instead, online, incremental, and active learning covers all those other aspects. So for the talk, I will just focus on the part of transfer learning. And we have to make a sort of shift also in the way in which we define, so in the formalism in which that we use to describe the tasks. So in standard machine learning, we think about training and testing data that comes from the same high-level distribution, right? So the standard hypothesis, everything is IID, everything is taken random from the same distribution, such that whatever you learn at training time, you can also apply it during the test and make some prediction. Well, in the case of transfer learning, you define something different. So you have a source, which is the distribution from which you take your data to train the model, and then you have the target, which is the application, let's say, setting, where the marginal distribution is different. So overall, the data are distributed differently. This is more the standard, actually, than an exception if you think in real life. Think about the case in which you look at a product online, high-level, so high-resolution images, white background, and then the model that you build from your web images you want to apply in real life, or with the images taken with your phone, right? So there is a clear domain shift, and you are in the source target condition. You want to make your model trained on, let's say, web images to work in real life. And there are several other conditions where you have this domain shift. Even just thinking about the axis of time, so if you think about what was a telephone 20 years ago, let's say that you have defined a model of a telephone, and then you want to use that model to recognize a telephone today, it's completely different. So there is a domain shift that you need to cover. In robotics, application becomes even more important because many models are trained in simulations, right? And then you want that these models are applied in real application to make the robot work in real life. And so again, there is a domain shift between synthetic images or synthetic conditions, simulations, to reality. Besides the case in which, let's say, source and target contain exactly the same set of categories, you can have conditions in which the source contains some set of categories, but then you want to still use this kind of information to learn a model for a new object. And you want to be able to exploit these sources when you have a limited amount of samples for this new category. Now, the global, let's say, framework of transfer learning is quite big. So it's a big tree, let's say. And everything depends on the, so you have sub, let's say, setting depending on how many samples annotated you have respectively in the source and in the target. So for instance, if you follow the highest line, you have that the samples in the target are annotated, but then you have a lot of samples in the source which are unannotated. So all the samples of the source are completely unlabeled. What you can do? Well, there is a process which is called self-flow learning. Nowadays it's also known as self-supervised learning. So you take your unsupervised source data, since it's a lot, you can train a big network with some exploiting some sort of intrinsic information, and then reuse this, the parameters of the network and fine-tuning on a few annotated samples of your target. Well, out of this big tree, we actually will focus on the case of domain adaptation, which is the case where you have a lot of annotated samples in the source, but no annotated samples in the target, and still you have to impose some sort of a high-level condition that the categories that you see in source and target are the same. And we will also see an intermediate condition, which is known as domain generalization. It's intermediate between domain adaptation and multitask learning. In the case of domain generalization, you have several sources, all containing the same set of categories, and you never see the target. So the only thing that you know about the targets is that it will contain exactly the same set of categories, but the appearance will be different with respect to any of the sources that you've seen before. Another subpart of transfer learning that I will briefly talk about is what is actually, so it is actually known as the real transfer learning, is few shot learning or one-shot learning, and is actually generally identified the transfer learning with the first block there, because it was the first one that was analyzed. So what happens is when you have to learn something new and you have just a limited amount of samples. So let's enter exactly in that framework. Let's say, as I was mentioning before, that you want to learn a model for a new animal that you have never seen before, and you have, for instance, 2 or 3 images, a very limited amount of samples. And you want to exploit the knowledge of previous models related to other animals. So how can you do that? Well, let's say that in 2009-2010, there were 3 groups working on this topic. One at MIT, one at Stanford, and one at PFL, and it was the one where I was actually working on. We came out with the first principled approach to solve this problem. The idea, in terms of it was still empiricalism minimization approach, so SVM approach, the idea is that you want to define the model for your new object, this W, and while learning this model, you also want to learn a linear combination of the previous models on which you want to rely. And you ask that the new model is close to this linear combination. So you have to learn W and at the same time also these betas. And there's a way to do it principally, so with, let's say, some basic guarantees. Now, what was super new in 2009-2010, then nowadays it's actually the standard. Because when you think about deep learning model, you never have a huge amount of data for your new task. Generally, what you do is that you have a network which is well trained on a lot of data, and then you re-exploit the parameters of the network when you have a new task. So this approach actually means that the inner part of the network, so the inner parameters, are actually reused, and only the ending part is updated. So it's learned again on the basis of the new task that you encounter. So this transfer learning actually nowadays is also known as fine-tuning. Fine-tuning generally starts from ImageNet, so you have a network which is very well tuned, very well trained on a lot of on this ImageNet dataset, which contains 1,000 categories and 1 million images, more or less. The network is trained, and then when you have a new task, you decide to update only the ending part, or maybe change the ending part because obviously the task is different, and fine-tune some layers. Everything depends on this fine-tuning process on how many data you have and what is the relation between the source and the target. So let's say between the new problem and the old one. Now, fine-tuning is not trivial. I mean, even though it's somehow the standard, it's not trivial, it's quite delicate because we have to understand what is happening inside the network. So at the beginning, we know that the starting layers of the networks are quite generic, right? So they are corners, edges, and somehow they can be applied to any kind of task, visual task. But then the ending part instead are very specific. So somehow in the middle, there is a point where we can decide to cut the network and keep it, and so we can still keep it, and the point where instead we start losing performance. And as I told you, I mean, everything depends on the relation between the source and the target, so how different is the target with respect to the source. These curves here that show a drop in performance are related to the case in which you take a network from a pre-trained model, so part of the layers from a pre-trained model, and the ending part of the network is completely learned from scratch. And so you see that there are still some drop in performance. But if instead of learning from scratch, you fine-tune, so you still keep the network as it was before, but you go on learning, in general what you see is that there is an advantage with respect to learning from scratch. So transfer learning in terms of fine-tuning seems to work quite well in general. Again, it depends on the amount of samples that you have and the relation between the source and the target. And indeed, there are some best practice, so some work that have analyzed how to decide if you want to freeze that part of the network or tune it, and this depends on, let's say, amount of images per class and the relation between the source and the target, which can be, quite similar or medium, let's say, on a medium level of similarity, or very similar. So, of course, how to measure the similarity is based on some evaluations that I will just give you briefly some idea afterwards of what are the measures to identify the relation between source and target. But before going into these measures, I would just want to give an example of a special kind of fine-tuning, because okay, we have said that fine-tuning works very well, but there are some cases where the difference between source and target is so big that thinking about just reusing the network pre-trained as it was, well, we cannot expect it to work. So let's say that you have your network which is trained on ImageNet images, so real-life pictures, and then you want to use that kind of information to classify objects when we have images from, let's say, depth images. So in this case, so images that you take with a Kinect, right? So the appearance is so different that you cannot expect that even just using fine-tuning, you can get something good. Well, what are the alternatives? Well, what you can do is say, okay, let's collect a lot of images, a lot of depth images, let's annotate them, let's create a data set big enough to allow us to train a new network. Or we can start thinking about something intermediate. So let's say the big difference between the source and the target in this case is due to the appearance in color, right? So let's think about coloring these depth images and then using these colored images to fine-tune a network. Is it enough? Well, maybe we can do something even more, smarter. So what about, instead of just, so the idea again is that of being able to reuse previous knowledge, but you have to do it with a little bit of thinking, right? So if instead of manually coloring the image, you introduce in the network, let's say some layers or a part of the network that learns how to color these images, what will happen? Well, it happened that actually learns something extremely useful to adapt to the task. So the idea here was work of my colleagues at PyCon in 2018. The idea here is to introduce, let's say, a learning block in the network that learns how to colorize the image. Then here we have a pre-trained image network, and the ending part is a new, let's say, fully connected layers that perform the classification. Now, once we have learned how to execute the colorization, even if we have images coming from, I don't know, I mean, a different setting, a different depth camera, a different data set, still we can reuse it because we have learned what are the important information of the way in which we need to colorize the image to then use this pre-trained model. It works well, better with respect to just using this color jet or predefined handmade, let's say, procedure to colorize the image. And besides that, you remember that I was mentioning before the fact that we introduce a sort of explicability. Well, the point is that we can look at what is happening inside the network and what kind of colorization we are actually doing. And it turns out that the depth images are colored in such a way to make appear in the image or to highlight in the image some parts of the object which are essential to recognize what is the object inside the image. So for instance, in the case of a keyboard, we start seeing the keys. Maybe the image is a little bit small, but in practice, the way in which we learn to colorize is highlighting some relevant parts which are helpful then at the end to perform the classification. Something that is not evident in the case in which you just colorize the image by hand. Now, this was, let's say, just an example, practical example of an extreme case in which fine-tuning by itself is not enough. And now I want to just mention this measure that I was indicating before. So we're saying we have a source, we have a target, but there is a big shift, let's say a difference between these two domains. How can we measure this shift? And this is important because then if we have a measure, maybe we can minimize it and let's say minimize this distance together with some other tasks, like for instance classification. Now, one of the popular measures to evaluate the distance between source and target, or this domain gap, is the maximum mean discrepancy. Now, I don't go into the details of the mathematics. What it's important here to know is just that it is a way to evaluate the distance of two domains, just considering the hypothesis that the feature lives in a space with some particular characteristics that have some, let's say, a metric space. For instance, the features which are extracted by deep neural network are living in this kind of space, and if the categories in the source and in the target are the same, what we can do is just averaging all the features in the source and in the target, and then measure, let's say, the distance between the mean of these two groups. So this is the source, here in this case as just positive, negative categories, positive, negative there, we have the mean, and then we measure the distance between these two. Now this is, let's say, a first order measure, but there are many others. So instead of just measuring the, let's say, the average and consider the mean, we can go and evaluate the covariance between the samples in the source, the covariance between the samples in the target, and then evaluate the distance between these two covariances. Now, the truth is that these two covariances do not live in an Euclidean space. So indeed, you should not just measure the distance with the Frobenius norm. There is something a little bit more complicated, but still, this is another measure to evaluate the distance between two domains. Even more, here I'm just mentioning it, just because it might happen that if you read a paper, you might encounter it and you might wonder what it is. This famous Basserstein distance, which is a distance used in many GAN methods, so the generative adversarial network, is a measure based on optimal transport. So let's say that you have a pile of sand, and you want to move each point of this pile of sand in another point. So move one point to the other, let's say, distribution. Now you pay a cost, which depends on how much sand, let's say, or earth you have in that point, and on the basis of the distance that you are moving this point. Now, if the mass of the two, let's say, pile of sands is the same, it's quite simple. When the mass is different, it becomes a little bit complicated. But still, this kind of measure based on transport is something that is also used to evaluate the distance between two domains. And then finally, is another measure which is very, very, let's say, used today is that of exploiting some sort of adversarial classifier. To understand how does it work, again, there's a lot of mathematics behind this, but it's, we can say in very simple words. So let's say that you have a source and a target, and you have the family of classifiers that you want to use to perform some sort of classification inside each domain. Now, if you use the same family of classifier, and you try just to distinguish between source and target, there can be two cases, let's say. One case in which the classifiers are able to separate source and target, which means that source and target somehow are far, right? Because if you are able to separate them, then they are quite distant. And then there can be cases, another extreme cases, where you are not able to recognize them. So the two domains are actually overlapping. So here there is a case of low confusion. So low confusion is when the two domains are far. High confusion is when the two domains are close. So in practice, what you can do is to use a classifier of the same family of the classifier that you want to use inside each domain to perform this domain classification and see if the domains are overlapping or not. If we want to apply this measure, to minimize this measure inside the network, what we should do? So again, we can think about the network as an initial part that extracts features and an ending part that executes the algorithm of classification, let's say, the exact classification. So if the two domains are very far, and so they are very different among each other, when you try to plot the features, the intermediate feature extracted by the network, you will see points which are grouped, let's say, in two different and separate groups. So for instance, red, which is one domain, and blue, the other domain. If instead the two domains are close, then you have a situation like this, so they are confused. So what we can do, we can actually use the features and impose some condition intermediate inside the network to ask the network to confuse actually the two domains. So these are just examples of networks. The first one exploits the maximum mean discrepancy. So source and target enter into the network, and once the features are extracted, then you ask that the, let's say, the maximum mean discrepancy between the source and target representation is minimized at different levels. And then at the same time, you also ask the source images to go till the end to the classifier, such that you learn a classification model. So this is used for MMD, then it's used also for the covariate distance measure that I was showing you before. This is an example that uses the Wasserstein distance. Well, there is also something else that we can do. So let's say that we are measuring this distance between source and target, and we are maybe moving the source towards the target or the target towards the source, at least to close this gap. Another thing that you can do is to consider a standard distribution and try to register the source distribution to the standard distribution and the target distribution to the standard distribution, right? So you consider a basic reference distribution like a Gaussian. And this is what this method is doing. So instead of adding an extra loss at the end, it is imposing some batch normalization layers inside the network used exactly to do this registration. As I was mentioning before, the most commonly used approach to reduce the domain shift nowadays is that of running this domain classifier, right? Is an image coming from the source or is it coming from the target? This approach, which is a domain adversarial neural network, domain adaptive adversarial, so it's a lot of A in the middle. But actually what it's doing is that the images enter into the network, the features are extracted, source features, I mean source images which are annotated, go to the end for the classification, and the features instead that are extracted from the target and from the source, regardless of the class label, enter this other part of the network, where what I ask is to distinguish if an image is coming from the source or from the target. Now, Of course, if we optimize the classification of the domain, so the domain classification, we tend to make the two domains the most different as possible, but this is not what we need. We need exactly the opposite. And so there is a gradient reversal layer inside the network that actually inverts the sign of the gradient and then asks that the features of the two domains are confused. Now, there are approaches so like this one, that tries to do the two things at the same time, so the task of classification and the task of domain shift reduction. There are some other approaches that do it in 2 steps, that in some particular cases might be beneficial. So this approach, which is approach from 2016, asks that the source images are, so we have a first step where the source images are classified, and then the second step where the target images enter into the, let's say, the process, but instead of running the classificator, here we have a discriminator just between source and target, and then the target CNN learned here, so the feature representation learned here, and the classifier learned there are combined together to obtain the final recognition performance on the target. Another example of 2-step adaptation is a process that actually is a work that I produced last year at ITER, again, it's a robotic conference, where again we have 2 steps, but done in a different way. So I first train a network to recognize if an image comes from a source domain or from the target domain. Now, once we have trained this network, we can look inside the network itself and try to understand which were the pixels more responsible for the domain shift. So for this classification, meaning that what we expect is that there will be some pixels that are somehow domain generic and pixels which are instead domain specific. So in these maps, what I observe is that the domain generic pixels, so the one that are not responsible for the classification, are the ones that focus on the object. Indeed, this was a task where we were showing the object to a robot, and what was changing was mainly the background. So in a condition like this, where the domain shift is localized, what I can do is exactly use this sort of attention map. So once I've localized what is the part of the image which is shared across domain, and I define the attention map, then I can train a new network just on the source images which are annotated, multiplying inside the network this sort of maps, so that the network will know where to focus to identify the object. Now, when is this kind of approach better with respect to just the domain adaptive neural network with the extra branch that we saw before? Well, in the particular case in which the target does not contain exactly the same categories of the source. So a robot might have a lot of images and a lot of categories during the source, let's say, acquisition process, but then at test time in the target, maybe it finds itself in a new house or in a new room where the number of objects is lower, it might happen, with respect to the condition in the source. So in this case, if we impose the domain adaptation process directly inside the network with the approach that we were showing before, so like this, well, actually we have a sort of negative transfer, because we are taking the old set of images in the source and the old set of images in the target, but there is a discrepancy not only in the appearance, also in the number of categories. So in this case, it is better to run a process with two steps. And indeed, it turns out that this first step is much less sensitive to the difference in the set of categories with respect to the approach that we've seen before. Now, what I've described here are methods that run domain adaptation in the case of executing an adaptation at the feature level, right? So inside the image. But there are other approaches that instead of waiting, let's say, to the feature extraction, run immediately a sort of adaptation at pixel level. All these approaches actually, there are some methods of this style adaptation also before the GANs approach, but in general, the idea is always the same. So the fact is that we want to let's say, change the style of the image visually such that it looks like the other domain. So I'm sure you have seen an example of this kind of stuff where you have an image with a content, and then you take the style from, I don't know, the Starry Night from Van Gogh, and then you want to apply that style on your image. It's true. I mean, this approach was before GANs, but then, well, actually it was after, but it was a little bit different. But indeed, nowadays the most used method to apply this sort of style transfer is the generative adaptive networks, where you start from an image. You apply, so you have a block here, a network block, which is a generator, which changes the appearance of the image, hopefully moving it from the, let's say, appearance of the source from that of the target. And then you have a discriminator, which tries to understand if the image is really coming from the target, so it's a real target image, or it's a fake one, the one produced by the network. And the two parts of the network, so the discriminator and the generator, compete with each other. Now, these kind of approaches are very nice. I mean, they were proposed originally just to produce images, so they were unsupervised. They were not caring about what was the content in terms of categorization or identification of the object inside. It was just to look at the images and maybe do some retrieval. For instance, you sketch an object and you want to buy something that looks like that, right? So you do sort of similarity evaluation to perform retrieval. But it was not strictly related to object classification. Afterwards, there have been work that tried to introduce also the idea of domain adaptation, so exploit this kind of style transfer to perform domain adaptation. In practice, what they were doing is just introducing a classifier in the network. So besides moving, for instance, a sample from the source appearance to the target appearance, then I also classify the image, because once I've moved let's say, the image from the source to the target style, then I have target images, or at least similar target images with a label, right, on which I can train a classifier. Now, GANs are nice, there are new GANs every day, and one popular approach recently has been that of using two generative adaptive approaches at the same time, which actually is, I mean, it makes sense, because what you can do is that you can take an image, use a generator that brings it to the, let's say, from the source, you bring it to the target domain, and then you bring it back to the source domain. And you have this sort of cyclic approach where you ask that the appearance of the image at the end looks similar with respect to the appearance of the object at the beginning. Well, again, this was applied just to produce nice images. Can we use it to do domain adaptation? Yes, and this was a work at CVPR last year from our group, where we actually were doing exactly that. So we're considering two GANs at the same time, from source to target, and then we have also the other way around, from the target to source. The interesting thing here, I mean, there are a lot of details, but the interesting thing is that we are not asking the image to just look like let's say, the source image that comes back to the source domain. It should not just look like the original one, but in particular, it has to maintain the same category. I mean, our goal is that to do classification, right, in this case. So let's say that we start from an image of 7, then we bring this, let's say, handwritten digit to street view house number. So it's colorful and it's a completely different kinds of style. Then we bring it back to the source domain. Well, we don't care if it looks like the original image. We care that it maintains the same categories such that the classifier will still be able to identify it as a correct image, as a correct label, and the correct category. Moreover, in this kind of approach, we had two classifiers, one living in the source domain and the other living in the target domain. At the test time, we were able to combine them and then exploit the ensemble, so the force of the ensemble approach. Till now we have seen several examples at feature level, or pixel level, of domain adaptation approaches, where again, I repeat it, the idea is that the source and target images contain exactly the same set of categories. The appearance change, but you always have one source and one target domain, and you suppose that the target domain, you have it at training time. It's not labeled, but you still have it because you need to close the domain down. There are more challenging conditions like that of domain generalization. Well, in the case of domain generalization, I was saying before, we have several sources still containing the same set of categories, and you want to extract the gist, the high-level information, the semantic information, such that the model that you build on this semantic information will then be able to work also in a new domain. How can we do that? Of course, it's more challenging, it's more difficult. So, what were the approaches for this kind of problem? Well, there are different kinds of methods. One that, so some of them, they try to separate for each domain, let's say, the source specific and the source generic information, and then trying to recombine them. So this is a little bit complicated model. It's called domain separation network, and you can also find all the reference here in the slide. But in practice, for each domain, you decompose source specific for each source. Here this is also applicable for domain adaptation, but for each source you separate domain specific from domain generic, and you impose some conditions. So for instance, the part which is shared and the part which is private for each domain, you impose a loss that let's say asks for a difference, a sort of orthogonality condition between the two. Instead, the two parts which come from two different domains and which are shared, they should be similar. And then you also ask that recombining back the specific and the generic part, you are also able to recompose the image, so to reconstruct the image, right? So let's say you extract features from the private or specific part or from the generic part, and then when you put together the two kinds of feature, from them you should be able to go back to the appearance of the original image. So there are multiple conditions combined together, and this was one of the first domain adaptation approaches so domain generalization approaches based on deep learning. Others exploit, for instance, some metric condition. Again, you have multiple sources. Each source contains the same set of categories. So besides asking for optimizing the classification loss and exploiting the labels, what you can do is asking that samples belonging to the same class but from different source domains are closer with respect to images that belong to two different classes even inside the same domain. So it is some sort of contrasting semantic alignment law, so it's a specific kind of metric condition that you can impose on the network, again, to allow to define the right metric to extract high-level semantic information from the multiple sources. Can we do even better? Yes. Or at least, is there something behind, let's say, multiple domains at a semantic level that we can exploit? Well, I asked myself this question, and I ended up with a sort of answer. I mean, there are some tasks that us as humans are able to do regardless of the kind of the style of the image. Think about solving a puzzle. I mean, you solve a puzzle, you are able to do it regardless of the fact that the image is a painting or is a picture. And what you do is that you use the characteristic of the, let's say, the edges of the image, you follow the lines, and so on and so forth. So there are a lot of information that you can exploit from the image to run this task. And this task, since it can be done regardless of the specific appearance of the original data, maybe we can use it together with the original classification to learn a model that generalizes well. And indeed, this is exactly what we did, and this is a paper that will be presented as oral at CVPR this year. So in practice, we have images coming from different domains, and what we do is that we decompose them in patches, and then we shuffle the patches, right? These shuffled patches define, obviously, for instance, if you have a grid 3 by 3, what you will have is a 9 factorial number of permutations. Well, what you do is that you just choose a subset of them on the basis of an algorithm, and the permutation that you have chosen, you assign to them an index. Now, what we get at the end is another classification problem. So given a shuffled image, you can ask the network which index you can associate, you need to associate to this image. So in practice, what we have is a network. Let's say the backbone can be whatever. It can be an AlexNet, can be a ResNet, can be any kind of standard deep learning architecture. And we input to this network. We give it two inputs. So the ordered image, the original ones, and the shuffled images. The ordered images go only into the object classifier, while the shuffled images, and also the original one, because in practice the permutation 0 corresponds to the original one, they go to the jigsaw classifier. So the classifier which identifies what is the correct permutation, right? So we are actually adding an extra task that helps the network to regularize and to learn more about the intrinsic characteristic of the images regardless of the domain. And it turns out that it works much better with respect to other competing domain generalization methods, regardless of the specific data set on which we actually test it. So here, for example, we have 4 domains. Every time one of the domains is considered as a target and all the others are sources. So we have art painting, cartoons, sketches, and photos. And overall, on average, we outperform with the other existing methods. Now, what is the network doing inside? So, of course, we are introducing a sort of regularization, but what is exactly, why it's exactly helping? Well, we try to make some sort of investigation, again observing which were the pixels more responsible for the final classification. And we compared the case of our method, which we call Jigen, with respect to dipole. Now, dipole consists in just taking all the images together, so in practice you forget about the green part of the network before, and it's just the blue one. Now, what happens is that when dipole fails, in many cases it fails because it does not know where to look inside the image. So this image has a label house, and dipole, identify the house, but also the street. Instead, Jigen actually understands that the most important part to focus on is where the house is. Because actually you are learning this co-location of patches, so how the patches are organized inside the image, and this helps to understand where to focus. Same here for the head of the person, or for the ears of the dog. And here it's very surprising because actually there's a giraffe here. It's very, very small, and our method is able to understand that where this important part to focus on. In the cases in which Jigen fails with respect to dipole, still the detection, let's say the most important part is found, but most probably there are other problems inside the network for which the final label is wrongly assigned. Okay, so we are using collocation of patches, so that's solving a puzzle. Is it the only self-supervised approach that we can use as a regularizer together with the classification to improve the generalization ability of the network? No. So we can find some other task, for instance, rotation. So think about your image, you rotate 90 degrees, then another 90 degrees, another 90 degrees, so you have 4 categories at the end. You ask the network to classify the object and to recognize class 1, class 2, class 3, class 4. If you do it, well, actually it still helps with respect to dipole, but it helps less with respect to Jigen. Well, we think this is related to the particular case dataset we are observing, because in practice, gravity, it's important when you deal with photos and maybe with paintings. But when we deal with cartoon and sketches, the horizontal axis is not exactly straight, so you can have a horse which is upside down and other kind of straight stuff. So in this case, Jigen is helping a little bit more. Okay, so there are a lot of other things that we can do with this kind of approach, because again, this kind of self-supervision is not related again to the labels, right? It's unsupervised. It's an inner information inside the image of how the patches are organized. And so even if the target contains a subset of the categories of the source, we can apply this kind of approach to run domain adaptation. We can also introduce some other particular tools that understand which are the categories that are actually absent in the target, and we show that by using our way of learning the features, we are also better able, with respect to competing methods, to understand which are the categories which are actually missing. Now, is it all of the story? Well, no, it's just the beginning. because there are many other applications where domain adaptation, domain generalization are very important. So here in the talk, I just focused on classification tasks. But again, I mean, I was mentioning at the beginning, what about semantic segmentation? What about scene recognition? And this, for instance, might be very important for autonomous driving. What about cases related to more, let's say, real world, so open world conditions? It's true that you can have a target with less categories with respect to the source, but it's also true that you can have cases where the categories in the target are more with respect to that of the source. And then you have to add something more in the network, which let's say disregard the extra categories of the target, or at least recognizes that these extra categories were not there in the source. And this is called open set domain adaptation. And both the semantic segmentation and open set domain adaptation were part of a challenge of the VISTA challenge of last year. So in practice, there is this domain adaptation challenge every year, that run every year. This is the third year, also in 2019. And I'm part of the organization of the workshop. So if you want to know more about how to participate in the challenges, let me know, and we can discuss about it. Well, images in terms of object classification, again, is not the only kind of application. We can think about application to the medical field. Transfer learning approaches have been applied also for recognizing poses of a hand from surface electromyography signals from different subjects, or applied domain adaptation for different kinds of acquisition modality in the medical area. There are works also in Mickey recently about this. And again, it's not the end of the story, because again, here we are focusing only on images, but naturally images relate to language, relate to sentences, relate to many other kinds of information, where domain adaptation and domain generalization may be still helpful. So this ends my talk. So I thank you for your attention, and I'm happy to take any questions.
When you were talking about your gig and work, and you say you were using a secondary task as a regularization. So you are also making another example, another secondary task. Did you try combining multiple tasks and to see if you put more of them together, they altogether improve?
Yeah, so we tried to combine, for instance, rotation with puzzle. For the task, I mean, for the data set that we had, it did not show any particular advantage. So, I mean, we can think about many other tasks, for instance, introducing some sort of odd one out. For instance, asking the network also to recognize if a patch is really belonging to an image, or it is an external patch. So we are working in this direction to understand if there are more self-supervised tasks that we can combine properly together to improve even more the techniques.
Yeah. Do you think we will get to the point where we will be able to learn a set of universal features and then forget about learning features and just move to it?
I'm not sure about that. I mean, this sort of universal features, till now, there's people that are already talking about universal features started from ImageNet. But I mean, you cannot think as that being the end, because, for instance, I've been working also on a visual question answering task. So if you need to answer a question, so you have an image and you have a sentence, right, which is a question asking something about the image. And then most of the methods, what they do is that they extract information from the image, ImageNet, based, what is called universal now, and information from the text, and then combining them together. Well, but the questions are difficult. So something are related to action, something are related to attributes. You cannot think that everything is ended just from the 1,000 categories extracted from ImageNet. So at the end there, we were working on finding a method to combine features extracted from ImageNet, but also from network that were doing action classification, color classification, attribute classification. So there are many aspects that has to be combined together. So I'm not sure if you're really close to this sort of universal solution. Yeah. Okay. So thank you again for your attention.